Confidentiality, integrity, and availability. These are the core dimensions, the three legs of the stool when we say protect data. How do we achieve these outcomes using the controls and capabilities of the platform is what we're talking about today. And then we're going to talk about how encryption can add yet another tier of not only access control, but also auditability and trust to achieve these same outcomes. Managing security means understanding least privilege. And least privilege means doing work. You can just give the accounting team, oh, well, here's the accounting bucket, S3 star. It's not the way to do it. It means understanding your workloads and understanding the principals who are going to be taking the actions to serve the business. Who are they? What actions do they need? To what resources? And under what conditions? PARC. Who is the identity? Where did it come from? Was the identity provider maybe on-prem, your Active Directory? You federate into the platform. Maybe you're building a workload with Cognito. Cognito is your identity provider. The actions, all of our services have very defined, detailed, granular, specific phenomena that you can do. List buckets is different than creating a bucket. You can let anybody list a bucket. Well, maybe not anybody, but maybe the whole team. But only certain people should be allowed to create a bucket. What are these resources? Am I going to give you access to all of EC2? Am I going to give you access to specific instances? Am I going to give you access to instances where tag department equals your team? And under what conditions? From what originating IP? From what region? And then there's service-specific conditions as well. You're allowed to create a bucket, but only with these characteristics. You can launch an RDS instance, but only certain engine types. We solve for this problem using declarative policy language across the platform. Policy language can be attached and of the principal, the actor, the identity. Policy language can also be attached to resources. So when we look at user policy, what are we going to do here? We're going to allow. What are we going to allow? EC2 attached volume, EC2 detached volume. For what resources? That is all of the instances, wildcards. But under what conditions? Only where department equals dev. Because the people that are going to get this policy should not be attaching volumes from the production. They should only be attaching the volumes that are tagged dev. And that is what this allows. This is a resource policy, same style of language, but it's not attached to the principal. It's attached to the resource. You can also use resource policies to grant and allow access, but here's a really nice example of using a resource policy to deny. Now, we always deny. We start with deny when we evaluate the policy language during authorization. And we authorize every single API call. There's no session. There's no session state. Every single time you call, we check. Every single time. So this doesn't grant any access. You may have been granted access separately as part of your identity, like the policy on the left. But the policy on the right that applies to a specific resource that's attached to a specific resource says we're going to deny all of the principals for all of the actions for this one bucket and prefix, right? Bucket name, prefix. Prefix is a little bit like a folder. It's the namespace. S3 is a key value store. For this particular key space, you must have multi-factor. If you make a call to S3 for any operation, for any principal, no matter who you are, no matter what policies you've been given, no matter what permissions you've been given, if you're going to interact with this resource that has this policy on it, for that particular prefix, you must present a multi-factor authentication during the call. Doesn't matter what other privileges you have. I could give you all the explicit allows on your identity. This policy protects this resource very specifically. So data is held in a lot of different places on the platform. We've got a lot of cool managed services, purpose-built databases. We announced some new ones today, and there's some really good ones there. Don't sleep on that. It's pretty exciting. RDS, Managed Relational Database, Aurora, bigger, better, faster version of RDS. And these resources are AWS resources. They have ARNs, and they can take resource permissions, but the data they hold inside of the engine is outside of AWS IAM. Now, you can manage the RDS instance, and you can manage the RDS snapshot, but if you've defined a user inside of MySQL, that is outside of AWS IAM. If you need to make sure your data is going to be durable, again, confidential, integral, and available, so snapshots are a great way to ensure availability. You can take snapshots and you can move snapshots to other regions for purposes of recovery, for purposes of resiliency or availability. Maybe the regulator's making you do it. You can even copy these snapshots into other accounts. Why would you do that? Because inevitably, your CRO is going to come to you and say, well, right. You have great access control, but what if you compromise the thingy that does the access control? You can place resources into a separate account with a different plane altogether as the, oh my God, break glass, at least we have this one extra copy, depending on your resources, depending on your requirements. But the data inside of the database is protected by the engine. Now, we've tried to make this easier for customers, and on a couple of the engines, you can exchange your IAM identity for a database user identity. And you can kind of map the database user identity to the IAM identity. We make this possible with MySQL. Really excited to see it ship for Postgres. But these credentials in engine, in your Oracle instance, your Oracle user, you've got to protect those credentials. If you don't protect those credentials, it's like you're not protecting the data. So how do you protect those credentials? Well, this is actually a super hard problem, but we solved it for you. We gave you a nice, easy, simple way to not only manage credentials, but to rotate them, and not just rotate them, but rotate them safely. So of course it's integrated with IAM, and you get the same really nice granular control on who can access the secrets and the credentials. Controlling access to these secrets is almost as important as controlling access to the resource, right? So if I allow you to manage this resource, or I deny you from managing this resource, but you have a login to the MySQL port, it's another dimension of protecting your data. When there's a lot of humans handling the secret, it really creates vulnerabilities. Don't put the secrets in the .password file in your home folder. Who's done that? I've done that. Don't do that. In automated rotation, the big value add here with Secrets Manager is what's fundamentally a workflow manager for rotating the secret. And why is that important? Well, number one, rotating a credential. I think we all kind of know rotating credentials makes sense in a lot of circumstances. You should probably end up doing it. But it's a dimension for availability. And maybe in your own life, when you've changed a password on your desktop and your phone still has the old credential, what happens? The phone keeps banging on it with the wrong credential and your account gets locked out. Anybody ever had that happen, right? It's a really ugly problem. So when you rotate credentials, you take on this dimension of availability, and that is really dangerous. So we try to make it safe. And Secrets Manager can help you safely rotate the credentials, and by making it safe, you can do it more often. We are already doing this today with EC2 instance profiles, where you can essentially inject an identity into the EC2 instance. The actual credentials, that is to say, the access key and the secret key, which is like a fancy username and password, for an EC2 instance profile, are changing throughout the day. Hundreds of millions of changes throughout the day on the platform of rotated credentials inside of our customers' instances. Heck, inside of our instances. We use AWS too. We rotate them constantly, and you never notice because it's safe. You never notice because it's integrated automatically through the CLI and the SDK. So here, we offer some Lambda templates to facilitate the rotation out of the box that works with all the RDS engines. And using the Lambda template, you can make it work for your homegrown database or whatever application that you've got. So of course, it's all logged and monitored, it's stored and encrypted. It makes it really nice to manage the credentials. If you are not solving for this problem, you are not protecting your data. So there's storage services as well. And of course, these hold even more data than the databases. We have S3, our object store, the Elastic Block Store, the virtual disk service that attaches to our virtual compute service, EC2. Glacier, of course, for long-term, and EFS, POSIX compatible. It's a nice filer, it's managed, it's highly available across regions, or across availability zones. And there's now more, as we announced this morning, Really excited about FSX. If you ever wanted managed Lustre, now you can have managed Lustre. It's pretty neat. So protecting data inside of these services takes on dimensions that are more tightly coupled to AWS IAM. So for EBS, the block store, for the objects themselves, for the volumes or the snaps from the volumes, you can write really nice tag-based policies as we saw earlier, where department equals dev or lifecycle equals dev. Durability, you can move snapshots around. As an implementation detail, snapshots are held in S3. So when you take a snapshot and we hold it for you, we're using S3. So you're inheriting the benefit of the durability of S3. And finally, the integrity is just we just solved for it. There's no bad blocks on EBS. There's no kind of corrupted. We're solving that as part of presenting the block device to you in the first place. In EFS, you can control the attachment of the file system using AWS IAM, but of course then there's POSIX file permissions to go deeper. EFS does not support ACLs, but it does support Unix style, Chmod style permissions. It works pretty well, and that solves for most use cases. Durability, again, you can take backups, move it around. EFS file sync, it's like a custom-built widget that we made. You light it up inside of your VPC. You can do all the pumping between EFS. We announced a new file sync service yesterday. It's a challenge for us to stay on top of what we have announced, what we haven't. We have a new file sync, so if you're coming from an on-prem filer and you want to pump it all into EFS, we make that easier for you now. And integrity is, again, automatically managed. For S3, confidentiality, as we saw earlier, we can write really detailed policies and require MFA. Durability, S3 is extremely durable in region. It's 11 nines of durability. I like to tell customers that those 11 nines are not a marketing number. Those 11 nines are a science number. It actually is 11 nines durable. We are not going to accidentally lose your data. You place an object in S3, it's the root of trust, it's the root of state. We're not going to lose it. You can copy your data out of region, CRR, move it to another bucket. Really nice, it's automatic, supports all the encryption. And we now can do selective CRR based on object tags. So if you just want to make sure you're automatically replicating the certain objects that have department equals controller, well, CRR now supports that. In integrity, automatically solved for. We have some very clever methods that we're using in this through storage layer to make sure that everything always is bit perfect. It doesn't decay, there's no bit rot. It's incredibly integral over time. So let's go deep on a very common access pattern. I've got identities in my virtual private cloud, and they need to access S3. 4 years ago, I'm going to light up an internet gateway. I'm sorry, did you say internet gateway to access my secure data? That's fine, it's TLS. Your security people don't like that. So we give you something called an endpoint. So you can reach S3 privately without giving internet access to all the instances in your environment. So how do we reason about the role accessing the endpoint, using the endpoint to reach S3? We have policy language, as we saw earlier, attached to the role. As it turns out, there's policy language that can be applied to the endpoint. That is to say, separate from the identity and separate from the resource that it's consuming, the endpoint has a role to play. And the policy language on that can further raise the bar, as we're about to see. And of course, we have bucket policy, IAM policy language attached directly to the resource. The IAM policy is primarily defining what actions this principal can take, as we saw earlier. Principal, action, resource, condition. This is what an IAM policy looks like. Saw this a little bit earlier. We're going to allow listing buckets. We're going to allow listing all the buckets, S3 star. We're going to allow put object, get object, and delete object, 3 different actions for this particular resource here, the reinvent bucket. On the bucket policy side, again, you can use a bucket policy to grant access, but it's often very nice, as we saw earlier, where we were going to deny, it doesn't matter unless you have MFA. It doesn't grant access. It makes sure that the access takes a certain pattern. Example bucket policy. We're going to deny all of the actions for all of the people except for the text documents unless it's multi-factored. It's the example we saw earlier. But the endpoint has some additional tricks. And the endpoint is a resource. So it gets a resource policy. And the endpoint can take policy language. And it can further constrain or allow the actions to S3 that cross the endpoint. So when we look at endpoint policy, this first one's really cool. It's got a new condition from us, principal org ID. This says we are going to deny all of the principals for all of the actions where the principal's org is not mine. String not equals principal org ID. That's actually my org ID in my house account, which is not a confidential piece of information, obviously. This means that if somebody brings in their home credentials into your environment and pastes their access key and secret key into their console, and they attempt to use their credentials to use the endpoint, it's going to deny the use of the credentials where the org ID is not mine. Really, really powerful for exfil concerns. Really, really powerful for if you got to allow maybe a partner to use your stuff. Least privilege. There's another stanza here. We're going to allow anybody to use S3, but only these resources. API calls using this endpoint to S3 can only regard those buckets. No other bucket. Not a different bucket in your company. It's certainly not your bucket at home. You can bring these together with further policy language on the resource itself. So let's look at how a bucket policy can regard an endpoint. We're going to allow access to a specific VPC. We're going to say, all right, on this bucket, anybody and all actions, we're going to deny you access to this bucket where it's not coming from my VPC. All API actions to this bucket will fail if they are not coming from my VPC. And you can also write it with not coming from my VPC endpoint. It would be weird to probably use both, but you can. Using both doesn't raise the bar, but you can have some options because you can ultimately deploy different endpoints inside of a VPC. But either way, the critical thing here is nobody can hit this bucket unless the calls are coming from your endpoint. This set of interlocking policies allows you to get really fine-grained and really specific to achieve least privilege. And that is how you protect data. You define principles, actions, resources, and conditions using our granular policy language to get the specific outcome that's required to prevent certain outcomes that, oh my God, absolutely, I will not tolerate. You can't use foreign credentials on my endpoint. Of course not. But there's a way to raise the bar further. Let's add encryption to the mix. We're going to do default encryption on a bucket. This is really nice. This took a long time to get out. This is something customers really wanted. So with default encryption, solves for a couple things. Number one, not only do your developers not have to remember to set encryption when they put an object, but if you've got third-party software that integrates with S3 but maybe didn't support encryption, that means you couldn't have used it if you needed encrypted outcomes. Well, now it makes it moot. This guarantees that all objects placed in the bucket, this is what the config looks like when you put it, we're going to enable server-side encryption. We're going to have it be the KMS version of server-side encryption. If you need to just tick the box, you can use SSES3, which is service-managed keys. Because customers typically want to raise the bar further, we're going to use my keys. We're going to use this specific key ID to get your encrypted outcome. So then the question is, well, why do you encrypt in the cloud? This is what people say. But what they really mean is that they need better control over their data. They want control with a key that I use, and they want to prevent unauthorized physical access. But this idea of providing this additional point of control is incredibly powerful because now, not only do you need the permissions to use the resources and the permissions to use the actions, you need the permissions to use the keys. To tell you more about that, it's my privilege and pleasure to introduce you to my friend, Ken Beard, the Director and General Manager of the AWS Key Management Service.
All right. Thanks a lot, Peter.
Captain?
righty. All right, so Peter talked to you about all the ways that you can define access control in terms of network-based access as well as the resource itself. Right? So if there is an Amazon resource name, an ARN, for the resource, then you can make that as a condition. You can build a policy on the resource itself, depending on the service, and you can control which identities will get access to that resource. A lot of people say, well, but I'm not quite sure whether or not I like that resource to be in plain text on disks in data centers that you will never let me visit in person. If you as a customer treat an AWS data center as a hostile environment, encryption is a best practice. Now, customers will say, all right, I know encryption comes down to where the keys are, and I sort of buy the argument that maybe I don't want to be managing the billions of keys needed to encrypt petabytes of data. And I could put those keys next to my data so it can be encrypted and decrypted quickly. So I sort of buy the idea of maybe keys being in an AWS data center. But dang it, I need to have control over those keys. That's what I tell my auditors. That's what I tell my customers. What does control mean in this case? So let me dig down a little bit. Here's the fundamental problem with having control over encryption keys. So with symmetric key encryption, this animation I've done several times in the past. So follow along. You take a key, you take an algorithm, you apply it to your data, you get ciphertext. That ciphertext can be stored anywhere on the planet. You trust that the use of a 256-bit key under the AES algorithm is going to produce ciphertext that is practically impossible for someone to brute force attack. Great. Store that wherever you want. However, you have a problem in terms of access control on that data because you have this plaintext key that was used. The algorithm is public. I just told you, it's AES. So where are you going to put this plaintext key? You certainly can't store it right next to your data, although that has some attractive durability properties. We don't let you do that. So where are you going to put it? In a different directory structure on the same host, or a different host, or somewhere that's far away from the data? Right, this is a hard problem to solve. The best practice in the industry is to protect this key the way you protected your original piece of data, is to encrypt it. So now I can put the data key required to decrypt the data right next to my encrypted data, two pieces of ciphertext. They share the same durability properties, and I don't have to worry about anybody who has access to that server host being able to decrypt my data. Problem solved, right? No. You've just encrypted a piece of data called a key with another key. So if you follow along, you just do this ad infinitum. At some point, though, if you want to decrypt your data, you have to have a plain text key somewhere that's always available to be able to decrypt data. So where is that key going to exist? So for the past approximately 40 years, the best practice has been we'll devise a specialized appliance called a hardware security module. And this hardware security module will have some interesting security properties to it. You'll notice it has very few ports. You'll notice that it has this special keypad device called a PED, where you as a human get to go and initialize the device and say, I now want you to create keys on yourself, and those keys will never leave the device. And anybody who tries to crack open the chassis will cause the system to zeroize all the keys on itself. So you would rather lose those keys than give up confidentiality. Right? These are very clever devices. And like I said, they've been used for decades by governments, by banks, by large manufacturing companies. But they are still a single device that has a single copy of a key. So you have to think about durability and availability of these things wherever your data happens to be that needs access to this high-level key at the top of the hierarchy to be able to decrypt your data. So the pros here is you control the actual device. You control how you authenticate to it with a username and a password or a certificate, and you control the user accounts and how the authorization to make use of keys on that device work. The best part, if you're in a regulated industry, is this looks very familiar to your auditing team. They've been checking boxes with FIPS 140-2 validated HSMs for years. So this is easy. However, if you are trying to build a geographically dispersed, highly available, highly durable application that can go up and down and scale to your needs, this is tough because you've got to procure these devices. And guess what? You don't get to put your hardware into our data centers. So now you're sort of stuck. And because the authorization and authentication mechanisms of these devices are using very bespoke, rather arcane cryptographic protocols like PKCS11 or JCE or CNG, right? That's not the language you use to talk to AWS services, right? You use things like signature v4 to sign API requests, and use things like JSON policies that Peter went through to define how you access resources inside the cloud. And this is true regardless of the cloud provider. So, second choice is maybe you take a dedicated HSM, but it exists in the cloud. So now you potentially reduce the time it takes to provision a device. You still control the authentication and authorization mechanisms, so your cloud provider can't see the passwords that you use. They can't control the crypto officer or the crypto user. You get to own that. Because this device is now closer to the EC2 instance or the S3 bucket in that particular region or availability zone, you get lower latency to cause that decryption to happen faster, the encryption to happen faster. Because we supply the HSMs here through the Cloud HSM service, we give you the opportunity to make an API call to cause another HSM to come into existence. Right? So again, you don't have to wait several weeks to procure one of these very expensive boxes from a rapidly diminishing set of vendors. Make an API call, and it shows up. And again, this looks pretty familiar to your auditors. It's FIPS validated HSM. In this case, it's supplied, the underlying cryptographic module supplied by a third party. This gets easier to check the box. But you're still stuck with, I can't make this work with AWS speak. There is no SIG-v4. There is no JSON policy document that works here. This is designed for your application, whether it's running in EC2 or on premises, to talk directly to this HSM to make use of keys. So the third option is something that we invented 4.5 years ago with the Key Management Service. And the idea is this is a managed HSM, so the key material itself is very safe, right? Cannot be accessed by humans. You also control the authentication and authorization, but now you're going to do it with signature v4 and JSON policies. You're going to treat keys inside this HSM. All the keys have an ARN. They're just yet another Amazon resource. You also get lower latency to your applications in the cloud, whether you're running them directly or they're running directly from an AWS service. And now you don't have to worry about scaling and making these keys highly available. It's our problem, right? You are used to approximately 20 milliseconds of latency on the decrypt path to gain access to a master key, right? You get that over time. That's our commitment to you. You're used to 4.5 nines of availability for all KMS APIs, right? That's what we want to do to make sure that you continue to use not only KMS, but also all the services that rely on KMS to encrypt your data. And because this service speaks SIG-v4, understands policies, understands IAM users and roles, we can integrate this very tightly with other services. So when you call S3 and say, S3, I want you to encrypt this thing that I'm inserting into the put path, S3 makes the call to KMS and says, I need a new 256-bit key to encrypt this brand new thing. But it's not me, the S3 service, asking for a key. It's actually customer A. It's their identity, their cryptographic identity, that wants permission to cause a new key to be generated. Or on the get path, to cause a key to be used to decrypt, right? So we're passing along your cryptographic identity directly to the service that holds your master keys. The big con is this does not look familiar at all to your auditors. What is a multi-tenant stateless HSM? Right? That's been one of the biggest challenges that we've had over the past 4 years, is to try to explain, we architected these HSMs, we built them ourselves because the commercial HSM market did not have a solution that would scale. We operate to the tune of tens of billions of requests on a daily basis. There just is no HSM on the market that can handle that, right? You can say, great, scale, deploy 1,000 of them. I challenge anybody on the planet to say they have 1,000 commercial HSMs in a production deployment. Frankly, there's not that much of a need for a single customer to have it. So we built the HSMs, we built the architecture, and we're trying to work with our auditors, our customers' auditors, our customer CISOs to try to explain the security properties of this service are very similar to what you're used to. Okay? How do we do this? Well, we say the service is designed so that once master keys are generated, the plain text copy of the master key is not available to anyone. It is simply not accessible. How does that work? Well, when one of our HSMs gets provisioned, when we launch a new region, once it is in active mode and it has generated its own set of keys that are then used to protect your customer master keys, there is no SSH to it. There is no telnet. There is no nothing. No humans have any ability to connect to that device to do anything. There is a very limited API, and only other trusted components in the service have the ability to call that API. There is no get key API. There is no extract key API. There's only, I want to use this key to encrypt and decrypt. Okay? The next question is, well, you got to update software. How do you do that on a running host? Well, we don't. We kill the host. And by killing the host, we wipe all the keys off the host. There is no more key material. And then we push new software to that host. And we do that one by one to make sure that we have the right set of keys to decrypt your CMK when you need it to be used. The next thread is going to be, well, what if somebody decides to push some malware to your HSMs and change the security properties of your devices? Introduce a extract key API. Yes, that's a very real concern, which is why we built these to require a quorum of authenticated digital signatures to be able to use the API, which is called update firmware. Right? So we make it a very loud, noisy, internally public process to update the firmware. We do this as rarely as we can get away with. Every time we do it, we are committed to resubmitting the new version of firmware to NIST under FRIPS 140-2, and you will see that our commitment inside our SOC control, which is now available for the fall 2018. We have a new control related to our commitment to FIPS, and you'll see the certificate from NIST. So we've designed a system that we think has the right balance between security, availability, and durability. The security properties, again, is our promise to you. How do you know that we're not going to change those security properties? Because we have to violate FIPS to do so. Because we have to violate our SOC and get a critical finding in our SOC 1 and 2. If you've read our SOC over the years, you know AWS has never had a critical finding in our SOC reports. That would be a catastrophic event. It would be a huge trust buster if we had a critical finding. So we are holding our own feet to the fire to ensure that KMS is as secure as it can be. Okay, so if you buy that the physical security of keys and the inability to compromise physical keys is fairly well designed, next question is, all right, how do I know who's going to use those keys? So, as I mentioned before, each CMK has a resource policy. It's called a key policy assigned to the key. What are the types of things you can express in a key policy using that principal, action, resource, condition semantic that Peter talked about? Well, you might say that these particular users and roles have the ability to use this key for encryption and decryption, either within the same account in which the key exists, or maybe some external account that belongs to another account in your IAM organization, or it could be an external account that belongs to a partner. Right? You are a service provider, and your customer is an enterprise customer that has an AWS account. They don't do much in it, but they might have a CMK, and they can block access to you, the service provider, whenever they want. They would grant you the ability to use that key only for encrypts and decrypts. This is how the integration with Box works. So if there's any Box customers in the audience, every time you upload files into Box, Box will encrypt and decrypt. It will go to KMS, and you have the option of saying, you're going to go to my key. If I start to feel like something hinky is going on at Box, I push one policy change, and now Box can neither read nor write data because they no longer have access to your key. So that's a good separation of control story. Another way to look at these policies is to control which applications can encrypt and which applications can decrypt. For those of you who have been doing crypto for a while, this semantic was often served by public key cryptography. You would give the public key to your encryptors and say, please encrypt data. I hold the private key. I'm the only one who can decrypt it. You can express that same semantic using a key policy and using symmetric keys. The administration of keys can be limited to a specific set of administrators. We strongly recommend that you think very hard about who has administrative rights to manage a key. And I'll go into a little bit more detail about that. You can share this key with an external partner account, as I mentioned, but only limit it to the use of encryption and decryption. And also, you can put additional conditions. So they only get to decrypt if they also pass in a particular string. Maybe it's an account ID. Maybe it's some other type of contextual information that is unique to that particular caller. And the language that we use for key policies is the same as IAM policies, S3 policies. The nouns and the verbs are a little different, and let's go through that. So here's an example of a key policy where the statement ID at the top is around access for key administrators. So if you look at the principal, again, this is an ARN of a particular IAM user. It could certainly be a role. It doesn't have to be a user. And when you look at the actions, the verbs, if you will, the ability to create keys, the ability to list them, enable them, and disable them, so control the state of a key, is very important. The ones at the bottom there, schedule key deletion, cancel key deletion, those are incredibly powerful APIs. Anybody who has the ability to delete a master key now controls the durability of potentially a petabyte of data in S3. So as you're creating key policies, one thing to consider is you just don't include that action. If that action doesn't exist, nobody has the ability to delete a key. But the person who has put star, and specifically put key policy, can go and update this policy later when you think you're ready to delete a key. And that could be a ceremony that involves multi-factor authentication, multiple people, right? These are potentially scary things to do. Now, the cost of having a key stored inside AWS KMS, $1 a month. Right? So this is not necessarily a painful thing to have keys lying around, but your auditors like a story of key lifecycle management, showing the birth, use, and death of a key. Okay, so now let's look at the use of a key. So this is much more common. Applications, end users, partners need to be able to cause keys to be used, even though the plaintext key material will never be exposed. So again, here we have, in this case, the principal is a role, and the actions are encrypt, decrypt, re-encrypt. Generate data key is actually a function where we generate a new 256-bit key, and we encrypt that key under the master key that you passed inside the generate data key API parameter. This is how envelope encryption works. Almost every AWS service that integrates with KMS, and that list is approaching 50 right now. Eventually, it'll be every service. We'll use this generate data key API so that individual keys that are scoped to the specific piece of data that you want that service to handle get their own unique key. Whenever you see resource star in a resource policy, just note to yourself, this is a reflective reference on the particular resource. This does not mean this is applied to all keys inside your account. Okay, so you've defined access control in the logical plane. and you agree that it might be a good idea for your cloud provider to host the physical key because it gives you great availability and low latency. But now, where does encryption actually happen? What are the choices there? So we have two basic choices. Client-side encryption. And in this case, this diagram's a bit of a mess because there's lots of options for where to do client-side encryption. If you start with, where is your plaintext data? It's in an on-premise system, or it's inside an application that you're running in EC2. You've got to pass it into some program that will perform encryption. That program is going to need a key, and that key can come from your own key management system. It could come from AWS KMS or Cloud HSM. Ultimately, it produces a piece of ciphertext, and then you submit that ciphertext to the AWS storage service, whether that's S3, whether it's EFS, any storage service that's going to take arbitrary data. Okay? So now, when you want to get that data out, you have to have the same client processes that can do the decryption dance. Okay? Server-side encryption, a little simpler, right? Your data starts at wherever. You call the correct AWS SDK to say, I want to put data in here, I want to write data, I want to, if it's Dynamo, you're going to do read-write, different verbs and nouns used for different services. But you're asking the AWS service to encrypt on your behalf. And you pass the specific CMK key ID to that service and say, make sure that when you encrypt this data, that the data key that's being used is encrypted under this CMK, because I have defined access policies on that CMK, and I want to ensure that only the correct people are able to write data into this bucket or read data from this Dynamo table. So you're allowing the AWS service to act as a proxy, passing your cryptographic identity to the place where the key exists to cause it to be used. Okay, so this is a repeat from Monday. So this is an announcement that we made Monday night. But for those of you who didn't catch it, because as you know, we do announce a few things here at reInvent every year, what we have done is provided another option for trying to find this balance between the storage of keys and the access policies for using keys. So we call this custom key store. And this is the simplest logical diagram. Let me go into a little bit more detail about how this works. So if you were to use KMS by itself today, the red key, if you remember from my diagram, that master key that wraps data encryption keys, it is made available at the time you need it inside a fleet of HSMs that we own. The way you call KMS, either from your own applications, via various SDKs, including the AWS Encryption SDK, or you ask an AWS service to call KMS on your behalf. If you were using Cloud HSM before Monday, you would again have some type of master key, a key encrypting key, created inside a Cloud HSM cluster, but now the interface to make use of that key is going to be limited to a set of cryptographic APIs. And if your application understands PKCS 11, that's great, right? If you're using something like Oracle Enterprise Edition with transparent data encryption, they've got a way to tie in to PKCS 11 and those interfaces. But you could not ask 50-plus AWS services to make use of that key inside the Cloud HSM cluster. Custom Key Store now enables that. Okay? So you call KMS and say, here's my CMK key ID. This is what I want to use on the encrypt path. KMS says, oh, I know where that key actually lives over in this Cloud HSM cluster that you configured earlier. And we will go from our service VPC into your VPC where the Cloud HSM cluster exists. And we will use a credential that you have given to us that gives us access to just that particular key on your cluster. So how does that process work? How do you set up this connection? Well, here's a screenshot of the console. Clearly, there's a set of new APIs that you can do this programmatically. In the left-hand side, you'll see there's a new option for custom key stores. And here you get to define an arbitrary name for the store. You are going to choose an existing Cloud HSM cluster. So this cluster has to have been created beforehand. And you can certainly read more about how easy that has become over the past 18 months as we've introduced enhancements in Cloud HSM. And then you are going to give to KMS the proper certificate that proves that it is connecting to the right cluster. So this is a cryptographic identity that KMS will use to ensure that the cluster ID that you selected is in fact the correct one. So this is the belt and suspenders approach. Then finally, you will have needed to have created a cryptographic user inside your cluster called KMS user. You will define a password for that KMS user. You will share that password with us the first time, right here, and then we will go through the process of rotating that password. So this is an important distinction because you're effectively giving KMS permission to connect to your bespoke Cloud HSM cluster, use a single key, act as a crypto user to do encryption and decryption events. You can also have KMS key lifecycle management APIs affect the key in your Cloud HSM cluster. For example, disabling that key, deleting that key, right? You get an independent audit log from Cloud HSM about all access to use keys inside that cluster, and that audit log, again, is not tied to an AWS service per se. It's another application log like you have inside EC2. You can certainly direct those logs to CloudWatch to make them easy to understand, but you're not relying on AWS to generate logs of key access through something like CloudTrail. So you can compare what you saw in KMS and the AWS service in terms of access to keys and therefore access to data and verify that with Cloud HSM. This can be a really interesting story for your auditors. So if you think about the various ways in which you can set up keys and manage them, there's what we call native KMS. You just call a create key API. We generate keys for you. No humans have access to those keys, and you control all the access. You can also import key material, so the BYOK feature that we launched a couple years ago, or you can have all your keys stored inside your very own Cloud HSM cluster. How do you know which of these is the right choice? Well, we've got a blog post that we published Monday night that might give you a sense for how to look at this. This might be the right conversation to have with your IT security team as well as your auditors and regulators. Or if you're a service provider and you do business with a large bank or a government or a large manufacturing firm, ask them what makes more sense to them. You can mix and match keys that are stored in different ways inside KMS. It all comes down to that key ID, which then you refer to inside your API calls. We keep track of where exactly that key material is used so that we can do cryptographic operations against it. So, trying to summarize kind of where Peter started with the access control on the resource itself, the network layer, how you combine some of that, how you think about the encryption of this information. It really does come down to access control policies. You don't get to worry about physical data security in the cloud. We've taken that away from you. We provide all sorts of assurances in our SOC reports that should give your own regulators and auditors assurance that we are doing the right thing. But the ability to read data and write data into your resources is entirely your responsibility. So you need to invest in understanding JSON documents that control access. The IAM team, if you've gone to some of their sessions this week, are always trying to find new ways to make it easier to get into JSON policy documents, understand the concepts, make changes. If you're trying to do this at scale and do it programmatically, you will appreciate the power of JSON and CloudFormation templates and these types of things. But it can be confusing at first. But this is where all of your security around access to your data is going to be linked. Because if you want to think about using encryption, again, all we're asking you to do is to manage access control policies. The physical security and all the assurances around the cryptographic operations, we do on your behalf. So one thing that Peter alluded to in his slides that I want to bring up, this idea of a database. We let you control who can spin up a database, who can cause an existing database snapshot to be launched. The data within that database, we don't know anything about. We can't necessarily apply an IAM policy to a social security number that exists in this particular field, in this particular table, in your MySQL database. However, you could use encryption to do access control on that. If you did client-side encryption of that social security number before you wrote it into the Dynamo table or the MySQL database, then you effectively are requiring the right principal to have access to the decryption key to be able to read that social security number. So it's a bit of a backwards way to think about using encryption as a way to provide granular access controls on data that AWS knows nothing about, and you don't want us reading individual PII inside your databases. But it's an indirect way to control access because the master key has to be available to the principal calling decrypt for that PII to be decrypted. Okay. So we've got some breakout sessions here. Some of these we've removed the dates because they've already happened. It might be useful for you to take a picture of this so that next week when you get back and you're going through the large library of YouTube presentations, you can type in particular session numbers here and understand more about how Cloud HSM works. If this custom key store feature is interesting, learn what it takes to set up a Cloud HSM cluster. Understand how secrets can be applied not only to securing data at rest, but also for transport security using certificates. So we invite you to take a look at all the features we provide, where again, at the end of the day, what you need to be responsible for is that resource policy. Okay, thank you very much for your time. Apologize for Peter and I coming from the Venetian a little bit late. Be sure to fill out your speaker sessions. Peter and I will both be available, if not here at the front, then out in the hallway if you have any follow-up questions. Thanks again.